Hi kids, this second video in our Changing Momentum and Forces unit is on SigmaForce and free body diagrams. The essential question for this video is, how do balanced and unbalanced forces on an object impact its momentum? We've been throwing the word forces around during the last unit or two because it's a pretty intuitive thing. It's a word we use in our normal lives. But we're going to, in this unit, make it a little bit more formal and official. What do we mean when we say a force? So for starters, force is a new variable. We're going to use the letter capital F to represent forces. And there will be lots of subscripts for different kinds of forces, just like we had subscripts for different kinds of energy in the last unit. Force is defined as a push or pull between two objects. And the units of force are really ugly. They are kilograms meters per second squared. But the good news is that physicists are lazy and they don't like writing all that out, so they have a shortcut unit, which is the Newton. So we measure forces usually in newtons. We've seen that sigma symbol before, but in this case, sigma F is a really important variable. It's way more important than any individual force, understanding what's going on with the total of the forces. So sigma F means the sum of all the forces. So you add up all the positive forces, you add up all the negative forces. Some of them might cancel each other out, and whatever's left is sigma F. So sigma F is like the total left over, the extra unbalanced portion of the forces. So there are many cases in the real world where all the forces acting on an object are balanced. Probably most of the things you see looking around you right now are experiencing balanced forces. Because if all the forces acting on an object are balanced, the object's momentum will not be changing. That, like I mentioned before, that doesn't mean that there aren't any forces. It just means that for every up force, there must be an equal down force, and for every left force, there's a right force or forces that are canceling it out. And so when those forces are balanced, an object's momentum doesn't change. You can write this mathematically. Sigma F equals 0, then delta P is also equal to 0. So those are the two big variables for this unit, sigma F and delta P. Of course, remind yourself that delta P, 0 delta P does not mean the object standing still. Okay, this could be an object moving at a constant velocity and still having a 0 delta P, and in that case, sigma F is still going to be 0. You can also look at the flip side of this coin. If you have an object that you know has no delta P, so an object that's moving at a constant velocity, like a train going down the track, for example, at a speed of 100 meters per second, that means that sigma F for that train is 0 as well. So all the forces on that train moving at 100 meters per second must be balanced out. On the other hand, some of the objects around us in the real world have unbalanced forces acting on them. And if the forces are unbalanced, if any of the forces acting on the object don't have an opposite force on the other side that's canceling it out, that means the object's momentum must be changing. So every time we see an object who is speeding up or slowing down or changing speed, the forces on that object, by definition, must be unbalanced. A way to write this more mathematically, if sigma F is not 0, so if the sum of the forces is not 0, then delta P is also not 0. So if there are unbalanced forces, momentum is going to be changing. One quick thing to note, that the momentum is going to change in the same direction as the unbalanced portion of the force. So if you have some extra leftover force upward, the object is going to experience a change in momentum upwards. If you have an unbalanced force to the left, the object's momentum will be changing to the left. The primary tool that we're going to be using in this unit to help us figure out what's going on with the forces and the motion of an object is known as a free body diagram. You know, in every unit we've showed you a few tools. We had MVP charts and we had before and after systems. In this unit, the tool we're going to be using is called a free body diagram, sometimes abbreviated FBD. A free body diagram is just a picture of an object, or it could be a whole system of objects, and the forces acting on that object or system of objects. So if several objects are connected to each other, you can include them all in the same object. You can lump them together. So even though a car has a bunch of parts, you could lump it all together into one single object. The purpose of a free body diagram is to quickly be able to visualize if the forces are balanced or unbalanced, And the reason we want to do that is because knowing whether those forces are balanced or unbalanced helps us determine whether the momentum of the object is changing or not. This is a big important deal. The reason free body diagrams matter so much is because they help us to explain the motion of an object in the past, and they help us to predict where or what that object's going to be doing in the future. So of course, being able to explain the past and predict the future is definitely important. So let's run through a sample free body diagram. In our free body diagram, first thing we're going to do is draw our object. So in this case, our object is an ostrich, but we're not going to draw an ostrich because it's complicated and takes up a lot of space. Instead, we're just going to draw a box or a circle to represent that ostrich. So that's my nice square ostrich. The next thing you add it to your free body diagram are the forces. In a free body diagram, the forces are represented by arrows. The direction of the arrow is showing which direction the force is acting, and the size of the arrow, how long the arrow is, shows whether the force is a large force or a small force. The first arrow I would probably put on there is downwards, because this ostrich is on Earth and we know there's a force of gravity pulling downwards on all of us. We'll talk more about those specific forces in the next unit, but probably most of you would realize that there's a downward force pulling that ostrich to the ground. There's also an upward force acting on that ostrich. That's the ground itself holding the ostrich up, so we're going to put that one in our free body diagram as well. Now, because this ostrich is standing at rest on the ground, we can actually make the prediction that those forces have to balance each other out. They have to be exactly the same size, because if they weren't, the momentum of the ostrich would have to be changing. In this case, sigma F and delta P are both equal to 0. No change in momentum, no unbalanced force. One way to show in our free body diagram that the forces are equal to each other, despite the fact they look about the same size, but you can also draw these little cross hatches. You may be using that same symbol in geometry to show that those two arrows are actually equal in length. Let's take a look at another free body diagram. This time I've drawn the whole diagram, and we'll talk about what we see on this diagram. This is a free body diagram of a toy car that's moving at a constant velocity. And a couple things to note about this diagram. We have that gravity force downwards, and this time I put a value in it. I said it was negative 14 newtons, negative because it's downwards. And the road is pushing upwards on the car, holding it up. And the value of that upwards force is also 14 newtons, equal and opposite. That says that we are balanced up and down, so that car isn't going to be changing momentum up or down. And I put those cross hatches on there to show that those are the same size. This car is actually also balanced side to side. So there's 3 forces on there. We've got 30 newtons going to the right. That's probably the force of the engine pushing the car forward. And then we have 2 different forces going backwards. We have negative 22 newtons and a negative 8 newtons. Maybe one of those is the friction, and maybe that toy car is either towing another car or someone's pulling backwards on it, or something is happening, so we have 2 forces acting backwards on it. Now, even though none of those forces are exactly equal to each other, they balance each other, because negative 22 plus negative 8 is equal to negative 30, which balances out the positive 30. So what we notice about this free body diagram is we've got a bunch of forces on it, but all of those forces are balanced. And because this free body diagram is balanced, that means we can predict that the car's momentum is not changing. This car is moving, but it's going to continue going at exactly the same speed because all of those forces are balanced. In this diagram, sigma F, so the sum of the forces, is 0 because up and down balance out and side to side balance out. And delta P is also 0 because the car's momentum is not going to be changing. Now let's take a look at a free body diagram that has unbalanced forces acting on it. So this is a free body diagram of an elevator, and you'll notice there's 2 forces on it. We've got the gravitational force pulling downward on that elevator, and we have another force holding the elevator up, probably the cables or the ropes. But something that's different about this diagram is those forces are different sizes. So I have gravity pulling downwards more than the ropes are pulling upwards on the elevator. What that means in terms of this free body diagram is that we have an unbalanced force, a sigma F. We have some leftover force in the down direction, okay, which we would call a negative sigma F. Because we have a negative sigma F, that means we're going to have a negative delta P. So our momentum will be becoming more negative. It's going to be increasing momentum in the negative direction. This actually could mean two different things about the movement of the elevator. If the elevator is moving downwards already and we are gaining more negative momentum, that means we're speeding up. So maybe this elevator is moving down and speeding up. That's one option. However, the elevator could also be moving upwards. If we have a positive velocity and a negative delta p, that means this elevator is the momentum of the elevator is becoming less positive, so we're going from like a momentum of positive 100 to positive 99 to positive 98 to positive 97. That's still a negative delta p, and that's an elevator that is actually slowing down, moving upwards. So you can't actually tell on the free body diagram which way the object's moving. All you can tell is whether the object's momentum is changing and what direction it's changing in. So let's try one last free body diagram that is unbalanced. We'll draw a free body diagram of Bryce Harper, who's a baseball player for the Nationals, sliding into one of the bases that he was stealing. So there's my picture of Bryce Harper. It's a nice box. But before I put the forces on this, I'm going to stop and think, what do I know about those forces and whether they're balanced or unbalanced in which direction? So as Bryce slides, his velocity is becoming slower. He was moving to the right and it's slowing down, so he's actually got less positive momentum. His momentum is changing in the negative direction. He's getting, less positive, which is the same as more negative. Which means that I'm expecting to see a change in momentum that is to the left, a negative change in momentum, which means we're also going to have unbalanced forces to the left. When we have extra force acting to the left on an object that's moving to the right, it's going to slow down. So these are the forces in that free body diagram. Bryce still has gravity and the force from the earth pushing upwards on him. Those are going to be balanced because he's not changing momentum up or down. But there is a single unbalanced force there, and that is the friction of the ground slowing him down as he slides into base. So you'll notice that this free body diagram is unbalanced. There's a big force to the left that isn't canceled out by anything to the right, and this is representative of a person who is slowing down as they slide into base. All right, please take a moment and summarize what you've learned in this slideshow. The essential question was, how do balanced and unbalanced forces on objects impact their momentum? Thanks for watching.